All right, good morning. I'm just going to get a couple more things set up. I've got a little behind the power curve this morning. I was trying to do an errand before I got started and ended up not working out very well. So, all right. Okay, today we are actually going to be doing some statistical tests. And the test that I've chosen to start off with is pretty much the first test that everyone starts off with when they start statistical training, and it is a t-test. So a t-test is a way of determining with a certain degree of probability whether two samples of numerical information are likely to have been drawn from the same underlying distribution by chance. So let me double check and make sure that everything is working. All right. Well, y'all will just have to tell me if the stream ends up sort of delaying because I'm having a hard trouble getting up. I'm having a hard time / also some trouble getting it set up so I can monitor it today. So do let me know. I've got my eye on the chat. Hi, Casper. But do let me know if you have any problems with the stream. So the sort of general idea is that what you get when you get a t-test is an idea of whether the difference that you see between two samples is just because of random chance in the way that they were generated, or whether it's really because they were actually drawn from two underlying distributions that are different. So if you want to see, for example, whether grade school children and middle school children are different heights, you could use a t-test to see that, with height as a numerical variable, and then the groups that you're comparing against each other would be grade school children and middle school children. Or I guess, I don't know what that would be in a different type of school system, but something like that. Hi, Blunky. Nice to see you again in the well, not see. I'm just gonna ask in chat real quick. Oh, there's my mouse. I was looking at it in the other window. Hello everybody. Welcome. I'm just waiting to see if people from the chat let me know that the stream is working. Let's see. You haven't missed anything. Sound is great? Okay, excellent. So I was just talking a little bit about the test that we're going to be doing today, which is a t-test. Hi, TJ. It is okay? Excellent. Thank you for your feedback, everybody. So what a t-test will return, among other things, and every sort of package will give you a different piece of information when you do it. But one thing that it will return is a p-value. So a p-value is, you can think of it as the likelihood that these two samples would have been drawn from the same distribution by chance. So if it's very, very low, we can reject the null distribution. We can reject the null hypothesis that there's no difference between the underlying groups that these two samples were drawn from. And I like to think of a really low p-value as sort of a one of the tools in my tool set when I'm building a statistical argument, but it's not the only thing, right? So you use some nice visualizations, and that's a tool to help convince people or explain to people what's going on in the data. You also probably want to tell people about the effect size. Like, it may be a very robust difference, but if it's a robust difference of like 1/8 of an inch in height or something that's really not that meaningful, then a really low p-value doesn't mean much, right? So there's been a lot of, if any of you are in scientific communities, there's been a lot of discussion about, well, should we do away with p-values, and what's, are these actually useful, and are they good science? And I think that they can be a useful tool, but certainly not something that you want to live or die by. So without any further ado, let's get started with R. So I've actually recommended some data sets up here in this part of the email, if you guys got this. Actually, let me zoom in so y'all can see a little bit better. I would recommend, if you don't have a lot of statistical background, looking at the cereals nutrition data set. And I'll say I sort of went through ahead of time, and sugar and sodium are both normally distributed. So there is an... there are a lot of assumptions underlying a t-test, and some of them we don't really need to worry about because Python and R can both take care of them for us, but it does have to be relatively normally distributed. And a normal distribution is when you make a histogram like we did yesterday. The histogram should look sort of like a bell curve, if you're familiar with that. So whoop. So you should have sort of this shape. It doesn't have to be perfect, but it does have to be sort of more or less in this shape. Otherwise, you will not get meaningful results from a t-test. So let's go and do this cherry-picked example that I have picked before. And there's also a couple of other ones that I picked that I think would be useful. So there's this really interesting museum, aquariums, and zoos data set. So you could pick out the institutions that are zoos and compare them to all of the other institutions and see whether zoos make more or less money. And you could see whether pink shoes are more expensive than other shoes. And you will notice that these are all comparisons of two groups because that's what you can do with a t-test. You can compare more than two groups with an analysis of variance, or an ANOVA, which is actually just a fancy t-test that has like some additional sort of folding. It's an ensemble. Casper asks, can you talk a little bit about taking the log of a variable in order to make it normally distributed across some point? Yes, I will actually make a note, and we can do that towards the end because I do want to make sure I get through just the first part, but yes. So taking the log is a type of normalization, which is when you take a non-normal variable and make it normal. Taking the log. Today I remembered to put a pen on my desk for normalizing. Mm-hmm. And there's a lot of ways that you can normalize things. Another way that people will do is to take a z-score, which is where you represent each data point by the number of standard deviations that it's from the mean, which may or may not result in a normal distribution, but can help squish some things that are further away from the mean. Anyway, so I don't want to get too deep into the statistics because there's lots of really, really good resources out there. I linked here to the Open Intro Stats textbook, which I really like, and they have a lot of sort of like labs, and I think the labs are in both R and Python. I know they have R labs for sure, but I think they also have Python labs, and the textbook and the labs are free. So if you feel called, feel free to go work through that textbook. I really like it. All right, so we're gonna need to start by making a kernel, as we do, and I'm going to use my example that I sent you guys, but y'all are welcome again to do this with other data sets if you like. What do I call these? Let's see. I think I called it 5-day. This is the day 3 channel. Yes, Padma, this is the day 3 channel. 5-day data CHLLANGE. Gosh darn it. Schwaz, man. This is day 3, and we're going to start with R, because R is my favorite. Also, it is much easier to do a lot of statistical tasks in R, because R is for statistics. That's what the language was designed for. So you don't actually need to import anything to do a t-test, because it's built into the language. But I'm going to be using tidyverse, because that's what I like to use. Import a library. Well, I'm glad that there isn't any buffering. Excellent. I have fixed that problem, which is good to hear. Import the library we'll use. Library. Tidyverse. Did I spell library correct? I did. Excellent. And we're also going to want to, let's call our data set, read in our data, serials, read underscore CSV, and this should look very familiar to everybody, hopefully. Oh, nope. So if you hit tab here, it will autocomplete with a list of files in your current directory, or since there's only one file in our current directory, the notebook source for the notebook that you're working in. So you can actually refer to the source of the notebook that you're using, which is a little bit of weird recursion. Input, and we just have the one CSV. And I always like to do just a quick head call when I there we go. When I read in a new data frame, just to make sure it read in good. Checking the first views. All right. Excellent. That looks good. And this data set was actually uploaded by Chris, one of my coworkers, so it's nice and clean. And there was actually, if any of you worked with this before, an older version of this data set, the first row was actually the data type of each of the columns, which is a little bit weird. But we have fixed that problem. All right, excellent. So that's the first part. And I'm just going to write a little markdown cell here so I remember what I did. First, today we're going to do a t-test. But first, let's read in our data and set up our environment. All right. And now we're going to perform, we're going to need another cell, perform our t-test. So the function for this is just t.test, which we can check out. And there is a little bit of is there a way to save the current notebook besides publishing? Galva asks. Yes, there is. So you can see at the top bar here, there's a little cloud with an up arrow and a little cloud with a down arrow. So the cloud with a down arrow will download the current version of your notebook. So whatever you see on your screen. So you can download your notebook and use it in a different program. And the cloud up arrow will allow you to upload a notebook file. Yes, it also saves. It also auto-saves. So you can see whether or not it has been saved by looking next to the Publish button. So you can see here my current notebook has been saved. But yes, if you wanted to save it, I don't know, to work, like if you're going to go on a plane and you want to work on it on the plane in like whatever environment you usually use locally to edit notebooks, you can do that. And I think you can actually do this with anybody's notebook. So if you wanted to download somebody's notebook and like, you know, make some changes and then upload it as a fork, you could also do that. Yeah, good question. Yeah, the interface does take a little bit of getting used to, but there's lots of nice little functionality, little features in there. All right, t-test. So there is a little bit of a choice here. So we are going to do an independent 2-group t-test. So we're assuming that our samples are drawn independently. So it's not like we measured somebody's height, and then we came back a year later and then measured their height again, because those two measurements would have a relationship to each other because they're on the same person. Whereas sort of one serial and another serial don't necessarily have a relationship to each other. And the syntax here, so this sort of like little tilde syntax is super common. Oh yes, absolutely, thank you. Gal asked if I could zoom in. So this little tilde syntax is sort of the syntax that gets used in a lot of statistical modeling in R. So this is sort of the output variable. This is the dependent variable, excuse me. And then everything to the other side, the right of it, is all of the things that you think will have an effect on this. So in this case, we're just looking at one binary feature, but if you get into fancier things, you can add, multiple features if you think they're all going to have an effect. So especially when you get into linear mixed effects models, you'll see a lot of like things behind the tilde, but the sort of general idea is this is the output and this is the input that you think might matter. You can also subsample your data frame, so you can have two vectors, one here, and that's another way to do the t-test. And if you do have a paired t-test, so that thing where you measure one person and then you measure the same person again later, in that case you would want in y1, the first item in the vector y1 is the first measurement for the first person, and then the first item in the vector y2 is the second measurement for the first person. Hopefully that makes sense. So you sort of go down and each across the vectors, each set of measurements is paired. But we're not doing that today. And this one sample t-test is if you know what the population mean should be. So you might say, so in the US we have census data, so we know what the average income is. So you might say, does this group of nurses at the hospital make more or less on average than the United States population? So that's sort of the general idea. And it's sort of a very foundational test. It's a little bit simplistic, but actually I found in a survey that I did of natural language processing that for statistical significance testing, t-tests were the most commonly used tests. So people do use it. All right, so the function is t.test. We don't need to load in anything. It is already in the R environment. And we were going to look at, what was it, sodium or sugar? See if I remember. Let's do sodium, because I think sugar is slightly more interesting. Have I checked for the normality of the variables? Yes, I did that earlier. So sodium and sugar are both normally distributed in this data set. That's a very good question, which is why I recommended it, because I went through and made sure that they worked good beforehand. So the output that we're interested in is, let's do sodium. And then, so I've just hit, so the $sign means within the data frame serials, I want to see a specific column. And the column that I'm interested in is sodium. How do you check? Oh, sorry, I did not read that very good. Yes, you check with a histogram. There's also, you can use a QQ plot is another way. QQ norm is the function. So I can, yeah, let me just do that real quick. Just so you can see what that looks like. So a histogram should make like a nice little bell curve, and the QQ norm serials sodium. So the sort of idea is that you want it to generally be on a line that goes along the sort of middle point. So you can see that there's a little bit of skew, especially like there's quite a few that have 0 sodium, but most of the data points are sort of more or less on a straight diagonal line. So I can actually check for normality with a QQ plot. And it does tolerate some non-normalcy. So we can, like, you can deal with a little bit of fudge, but if you made a QQ plot and it was like it looked like an S, then you wouldn't be able to use a t-test. The QQ plot, if normal points should be more or less on the center diagonal. There you go. Yeah, that is a good question, because you do want to do this with things that are more or less normal. All right, so we are looking for the output. The dependent variable is sodium, and the thing that we think will affect how much sodium is in it is whether or not the cereal is hot or cold. So we can see, scroll. Actually, we can see here in the head. Well, you can, but so there's the type of cereal, and it's either C for cold or H for hot. So there's two groups, which is good because that's what we need. And this, actually, let me add a little bit of narration because it's not super clear what this means. Is there a difference in the amount of sodium across the two types of cereal, hot and cold? All right. So the output, there's a lot of nonsense. So this is the actual value of the t-test. So it does put out a number, and then the whether or not that is significant depends on the number of actual samples that you have. And then here is the degrees of freedom, which again depends. So this is a measure of the number of samples that you have. And this is the p-value. So depending on what p-value you've decided ahead of time to use to set the difference between these two groups, you might either fail to reject the null. So if you said that you wanted a p-value that was below 0.01 and that's what you would find convincing in this instance, you would say, well, nope, it's not below that. We can't be sure that there is a difference between these groups. If beforehand you decided that 0.05 was your target p-value, then in that case you could say, yeah, I'm pretty sure that there is an actual difference here. And here you can see the difference in the means. So when I was talking about effect size earlier, this is what I was mentioning. So if there was a really robust difference, but the mean of group 1 was like 1.65 and the mean of group 2 was 1.67, and it was very robust and reliable but very small, then it wouldn't be a very interesting difference. So let me actually add a little bit of narration here so that we can come back and remember what we were doing here. So if we set our p-value to 0.05, let's say if we decided oh yes, df is degrees of freedom. Yep. So if we decided to set our p-value to 0.5 before we started, we would reject the null, i.e. can be pretty sure that there's not a difference between these two groups. T is the actual value of the t-test. df is the degrees of freedom. And the p-value is the likelihood that we would get a difference actually it's the probability, sorry, not the likelihood, that we saw a difference this large between our two groups just due to chance if they were actually, this is a lot of typing, if they were actually drawn from the same underlying population. All right, we can, comparing the means, it looks like there tends to be much less sodium in hot cereals than in cold cereals. Awesome. Any questions about this so far? Is it pretty clear? I know that there's lots of sort of very exact language in here, which is just because I want to be very clear about what a t-test can and can't tell you. Yeah, so I'm gonna sort of pause for a second and let you guys ask any questions if you have them. And while that is happening, I'm actually gonna do a little bit more narration in here, just so you can go back and look at this later. We should make sure that the variable, what T and DF are for. So we actually aren't using them. So if you've taken a statistics course and also took it like a little bit a while ago, so for every degree of freedom, the distribution of T values is different. So the reason that you would use these, so T is a measure of the difference between the two groups. So if T is very large, there's a large difference. If T is very small, there's a small difference. And back in the day, what you would do is you would take your T value and you would take your degrees of freedom, which you had calculated by hand. Oh, I am starting an R, and then I'm going to go do Python. And then you would go and you would look up in the back of your stats textbook for like the table with the X degrees of freedom. This T value has this P value. This value for the t-test has this p-value, so it's a way of figuring out this likelihood, which you could calculate by hand, but it's rough, which is why we do this with computers. And I will also make this notebook available, so this is the title, and it's on the cereals data set, and we're about to do Python. Is normally distributed. Spoiler, I checked that it was beforehand. So let's use a QQ plot to do that. All right. And then I'm just going to one more cell, and then I'm going to make this public and publish it, and then we're going to go on to Python. Perform our t-test. And the extra credit assignment, which I will get to at the end if we have time, is, no, this ain't it. The extra credit assignment is to plot 2 histograms, one for each group. So separate your data set into 2 groups, plot 1 histogram for each group, and then look at them with your eyes and see whether or not they are different, and whether or not you find the t-test to be parallel evidence. All right, let's publish this. And then we're going to do the exact same thing in Python. Yay! So if you guys have been watching before, you may know that R is my preferred language for this type of thing, and that Python is not my preferred language for this type of thing. So it's going to be a delightful learning experience for all of us. And for Python, so another assumption of the t-test is that the standard deviations of the two groups are the same, and that almost never happens. Like, that never happens. So the r-t-test assumes that there isn't the same standard deviation between your two groups just by default, so we don't have to mess with that. The t-test underscore ind function from scipy.stats, which is what we're going to be using, does assume that the variances are equal. So let me zoom in a little bit so y'all can see. So you can see this is the default values for this particular test. So it assumes equal variance is true. And we probably want to set this to false because, again, it never happens with real world data that the standard deviation is the same. Unless you have the world's largest data set. I guess maybe like census level data, the standard deviations might be the same, but it's pretty rare. I'm just waiting for this to render. You know, I can start a new notebook. That's no problem. While we're waiting for this, let's go to the data source. I just want to click on it. Kaggle.com /datasets, and the serials dataset is what I was using. So now we're going to do the same thing in Python. So we've looked a little bit at what the function we're going to be using is. Oh my goodness, it's really slow. So what was the conclusion? Well, the conclusion would, oh, that's not good. The conclusion was, so it is saved, so I'm not worried about losing any work, but let's try refreshing it. So the conclusion would depend on what you had set your p-value as. So for a data set this small, I probably would set it to 0.05. So if that's how so if your p-value is 0.05 and you run 20 tests, one of them is likely to be wrong, right? Because it's the likelihood that you would see a difference this extreme from by chance if you were actually drawing from the same underlying conclusion. So people generally set the p-value lower if they have larger samples and if there's less room for you to actually be wrong. So in medicine, for example, like you have two groups of people, one of them takes the medicine, one of them takes a placebo. You want to be really sure that the medicine actually helps, right? Or that the difference between these groups actually is due to this medicine. So in medicine, the p-values are usually set very, very low because there's very low tolerance for being incorrect. Oh, so you don't actually have to do anything. So Srinvaksha asks, can you please show me where to set the p-value? In your head, in your mind. So it's just a decision that you make. Sorry, yes, thank you, Abs. You're actually setting alpha, which is the level of the p-value. Yes. So whether or not you accept that there is a difference or not depends on, you know, the argument you're trying to build, your willingness to be wrong about it. So yeah, and that's just a personal choice. Which I know that statistics is supposed to be like, oh, and now we just know for sure. But it's unfortunately cereal? Is that not how you spell cereal? I know the dataset name starts with cereals. There we go. Oh, wow, it's not how you spell cereals. Wheel. All right, and it's running. Let's just try publishing this. Make sure I didn't lose any work. Yeah, no, look, looks good. So we're going to start a new kernel in Python. And it is called this. And let me, oh my gosh. Oh, why can't I select text good? And I'm going to make this public so you guys can work with it as well if you like. And this one's going to be in Python. All right, so we're going to do the same thing all over again. So first we're going to load in our libraries. And then we're going to import pandas, and we're going to alias that as PD because that's what everyone does. Yes, thank you, Hap. So Hap says alpha is the significance level or 1 minus the confidence level. And so we are going to actually alias just, we're just going to import just this one test that we need because we don't need the whole package. Pandas for data frames. Just the t-test from scipy.stats. And then we're going to read in our data and then check out the first few lines. And that is PD. Oh, let's give it a name first. I call it serials, I think. PD.read_CSV input. Nice. And now I have to remember, I think it's the data frame dot head. I think this is an attribute and not, I think it's a method and not a function. Yeah, excellent. One of the things that I personally find coming from R, I find frustrating about Python is that the difference between functions and methods, which are both functions, but the syntax for them is different. So if you misremember what something is, it doesn't work. That's okay. I'm getting there. It is a method. Thanks, Apps. Padma asks, how do you read a data set if it's local and not on Kaggle? So Galva, yes, I do make the menu pop up with a tab. So yeah, if I hit C and then hit tab, I will see all the things that I could type that start with C. If your data set is local, you can't access it on Kaggle, unfortunately. Yeah, you can upload your own data sets. So this is public now. So if you go to datasets, you can just start new dataset and you can upload your files. So if you want to work with them on Kaggle, you can do that. But right now there's no way for Kaggle to access the file structure on your computer, which is just as well. You don't necessarily want that. That's a little bit of a security problem. And since I did a QQ plot in R, let's do a QQ plot in Python, which I don't know how to do. So this will be a good learning experience for me. Oh, it's in SciPy. Excellent. So we can just, let's see, scipy.stats.probplot. Was there a lot of syntax after that? Not a whole bunch. Okay, I'm gonna do the time-honored copying and pasting from Stack. So from Stack Overflow. Import. Oh no, I just want to import probplot. Probplot for a QQ plot. QQ plor. All right, and now we're going to do a QQ plot, and we did sodium last time, so we're going to do sodium again. Okay, so this is just them creating a dummy variable. So we can just do that, except we're going to have to replace this with the variable that we want, which is cereals. And then from cereals, we just want the sodium column, which is not going to work if I don't spell sodium good. What if I just get rid of that? Do I need that? Well, that's not a plot. That is a list of probabilities. Meh. Oh, so it needs PyLab as well. All right. Import PyLab. You need to import matplotlib.pylab. Thanks. Whip. No, I don't want to go down. The magic command percentage sign. I'm not familiar with the magic command. What am I doing? Import matplotlib dot pyplot. Nope. Matplotlib dot pyplot. As plot. Also for a QQ plot. Let's see if this works. Oh, so here's a little weirdness is that you can undo things, but only within your current cell. Okay. The magic command is already on for the Kaggle notebooks. I've never heard of this. I have no idea what this is. So just like matplotlib, and then you don't have to import anything? Or like after it? Anyway, we're getting off track. We're getting off track. Plot a QQ plot to check normality. Without it, Python doesn't show plots. You don't need to call plot.show. Oh, I see. So it looks like Python doesn't render plots by default. So if you use a Jupyter notebook and want to see plots inside the notebook, you must put %sign matplotlib in line. Okay. So it looks like Kaggle will automatically always render the plots, and this is something that's Jupyter Notebook specific, but we don't have to worry about on Kaggle. That's what I'm getting from this. You can tell how much I use Python. Most of the points should be along the centre diagonal. If the variable is normally distributed, most of the points should be along the center diagonal. Excellent. And so you can see there's like a little bit of weirdness, mainly because some cereals have 0 sodium, but most things are mostly along the center diagonal. So I am personally convinced that this is normal enough. All right, so now we're going to do our t-test, which I believe is t_test_end. Excellent. And I don't know what it wants in terms of a data structure to put into it. But I do know that I want to make sure that it is not assuming equal variance between the groups, because almost never will that be true. There we go. So it is expecting the means of 2 independent samples of scores. 2-sided test for the null hypothesis. That makes sense. So 2-sided means you're just looking to see if they're different. You do a 1-sided test if you were sure, what you were interested in is A bigger than B, or is A bigger than small. So it wants 2 columns, A and B. So what I'm going to need to get is get the sodium for hot cereals, get the sodium for cold cereals, and then compare them. So I think I might be able to do because so this is the way that this data is structured is that the type column has what's the word I'm looking for? Has the binary variable in it, and we're interested in the sodium column. So I think I should be able to do cereals and then type equals C. Is that an uppercase C or a lowercase c? It's an uppercase C. And then let me actually do this in a new cell, just so I don't have to run the whole thing. If I could type good, this would be easier. All right, and then I think I should be able to do cerealis sodium, and then just the ones where that is true. Yes, excellent. It works. And Haps points out you can also check for normality in Python using ks test underscore normal from statsmodels.stats.diagnostic, or normal test from scipy.stats, or Shapiro from scipy.stats. So you got lots of options. Oh, excuse me. All right. But we are doing this the dumb way. So this is, we're going to call this variable, actually this one's hot cereal, so we want that to be an H. Hot cerealis. And for this one, we're going to call it cold cereals. So what we're doing here is, and this should be C. So what we're doing is this looks through the type column in the cereals data frame and finds for each cell, looks and sees whether or not it is equal to C. So it looks inside and says, is it C? Is it C? So this particular thing that we're passing it. And if it is, then it hands us a true. And if it isn't, then it hands us a false. So this gives us a vector of Booleans. So it's either true, true, false, 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 true, 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 false. And what I'm doing is I'm taking that vector and then passing it to the sodium column. So it will ignore the things where in the type column the cereal type is C, so it won't give us those. And then when it isn't C, so when it's given me false, it'll just ignore that row. When it is C, so when it's given me true, it will grab that row. So this is just a way of filtering. And I'm sure there's more elegant ways to do them in Python, but this is how I know how to do it. So hot cereals. Oh, this is not going to work if I don't remove that little thing. Hot cereals, and then cold. Oop. And somehow I just typed insert. And then cold cereals. EALS. And then so we're going to feed each of those into the t-test. So it's comparing this list of values, so the sodium for the hot cereals, to this list of values, so the sodium for the cold cereals. Hopefully that makes sense and everybody followed it. And hopefully this works. Yay, it did. Excellent. So we got actually the same result, which is good. We would not expect not to. So here, statistic is the t value that we got. It doesn't tell us the degrees of freedom, but it does tell us the p-value, and the p-value is the same that we got the last time. And what I'm actually going to do is, I'm just going to copy and paste the duration from the other notebook so I don't have to type a lot more things, because typing in public is awful because I'm bad at spelling. Anyway, so again, if you set your alpha to 0.05, this is below 0.05, and if you decided beforehand, I'll take a 1 in 20 chance of being wrong about this, then you can accept this. If you decided beforehand, no, you know what, this difference, I really want to be sure about this, and I only want a 1 in 100 chance of being wrong, or a 1 in 1,000 chance of being wrong, then you'd reject this because you don't have great enough certainty. Yeah, I personally find the output from this test is much less helpful. Like, I like to know the degrees of freedom. I like to know the means of the different groups. But shrug, your mileage may vary. If you're more comfortable in Python and this is a better way for you to do this particular task, then I don't want to dissuade you from doing that. Except I have to delete that thing about comparing the means because we can't compare the means. To set our alpha the highest p-value we would the highest p-value we would allow that would still allow us to reject the null. All right. Excellent. So we don't see the means for each of these groups. So let's actually just plot the means just to make me feel better, because that is something that I think you would want anytime you do a t-test, is you're really looking to see whether the means of these groups are different. So you do want to know what the means are. Mean? Is that a function? Mean hot cereals. Let's try this. Nope. Maybe average? Nope. Maybe average? Nope. Maybe mu? Nope. Okay. Let me look this up. Hotcereals.mean. It's an okay. Thank you, Habs. And also Galva. And also RS Mellow. Y'all are lifesavers. There we go. So it's one of them methods. Why are there two ways to do functions in Python? I'm sure there's a good reason under the hood, but it drives me nuts. Cold cereals.mean. And I do want these both to print, so I'm gonna put them in a print cereals. And I'm actually gonna do another thing that I like to do, which is do another print right above it that tells me what I just printed out. Mean sodium for the hot cereals. And then print mean sodium for the cold cereals. One of these is misspelled. I think it's this one. And then I do also want to print that. And print. And because I want, well, I might just do it without a blank line. Means, blah, blah, blah. I have made an error. Oh, that's because means is nothing. That's nothing. Let's look at the means, averages, of each group to see which is larger. All right. Excellent. How much time do we have left? Just got about 7 minutes. I kind of want to do the extra credit and plot it. What do you guys think? Should we do some plotting? Crickets. I want to do some plotting. We're going to do some plotting. Yeah, Galva wants plotting. Excellent. Plots it is. And I'm going to do this in R first because I know how to do it in R and it will be very fast and beautiful. And then the Python. So we've actually already done a little bit of plotting. We did them QQ plots, which are an important diagnostic. And we're going to do our t-test and get our nice output. And now we're going to do another cell, and we're going to plots in Python. Well, it'll, in very short time, because this will not take me a lot of time in R, plot a histogram where each cereal is a different cereal type. Hot versus cold is a different color. And we have already imported ggplot because that is in the tidyverse, so we can just do ggplot. And then our data is cereals. And then our aesthetics, the X aesthetic is going to be sodium. And the color is going to be type. Does it have a capital T? It does not. Equals type. And then we're going to add geom. Oh, sorry, zoomed out. Geom histogram. And then we're gonna add GG title sodium content by cereal type. And this should work. Yeah, nice. So what we can see from this is that we have a fairly unbalanced sample. So this bar here that's outlined in blue and this bar here that's outlined in blue are the hot cereals, and the rest of these are all cold cereals. And actually, rather than color, which is the line around the outside, I'm going to do fill, which is the color of the bar itself. Yeah, excellent. So this is the, we can see that this is sort of an unbalanced sample, but we can also see that the cold cereals tend to have a lot more sodium. And in fact, most of the cold cereals have 0 sodium. All right, that was easy. Python time. Alrighty. Let me add a little cell here with some markdown. Now plot a histogram for each cereal type. And I'm gonna go back and look at what I did the other day. Actually, let me publish this really quickly so you guys have access to it. Let's see. Kaggle.com/RC/5-day data. It's not auto-completing. I don't think I can get to that. Let's see. Let's see. Mine, day 3, day 3, day 2, Python. There we go. Plot 2 histograms at the same time with Matplotlib from Stack Overflow. Thanks, Habs. That is exactly what I was going to type in. Oh, looks pretty good. Ours isn't going to look that good because we don't have a very balanced sample. Overlapping bars. I'm okay with overlapping bars. Yeah, I'm fine with that. We don't need to import random because they're just doing that to do this generating random things. I'm not going to do this numpy.linspace to determine the optimal number of bins. I'm just going to wing it. So let's do this. So they are importing from Matplotlib, they're importing pyplot. And I think we already have pyplot imported. Let me double check. Oh, we do not. Okay, no, yes, we do. We've just aliased it as PLT. So we need to change all of these to PLT. Yep. As Haps also just pointed out. And I don't think we need to do show. I think that's what we determined. So we just need to do this to hot cereals. And I am going to keep this alpha hot because I think that's what makes the bars transparent, so you can see the one that's underneath. So hot cereals and then cold cereals. And we don't need bins because we haven't calculated that. And let's label it as cold. And let's see if this works. Oh, okay. That's because that's not the word that I meant to type. Name pult is not defined. Well, it should be. Let's try it. Let's try rerunning that and see if that helps. Yeah, nice. Oh no. Oh, poor hot cereals. They're just like these horrible little blips. Yep, sure it was a typo. Now plot a histogram for the 2 cereal types with each as a different color. All right. Plot the, and actually what I want to do is I think I want the hot cereals to be plotted second and not to be transparent, so we can actually see them a little bit better. I think that will help. Yeah, excellent. So the alpha is what makes these sort of see-through, so taking that away makes them not see-through. And then these are, just like ggplot, these are each adding a layer to the plot, so I have moved this one, the hot cereals underneath the cold cereals, so cold cereals gets plotted first, and then hot cereals gets plotted on top of it. So, plot the cold cereals and the hot cereals, and add a legend, and we also need a title. Add a title. And we should also probably label the axes, but it's 9:30 now, so I might not. It's plot.title, right? Yeah, it is. Count of cereals. Sodium content. Sodium content of cereals. I'm gonna put a little milligram here so we know the units by type. Nice, excellent. So we didn't get a chance to talk about log normalization, but so I'm just thinking about all the things I have to do today. I might have a chance to put together just like a little sample notebook that shows some normalization techniques. So I will tentatively say that I'll do that. Oh, and I don't have my notes here. There was something somebody was asking about on Monday, the Graph Lab interactive thing. And yeah, unfortunately, we're not going to be able to use that on Kaggle because of licenses. So, all right. You're very welcome, Galva. I can hang around for a couple minutes if anyone wants to hang around and ask some more questions. But otherwise, that's pretty much it for today. Thanks for joining me, and I hope you guys learned something. I certainly learned something. Man, this Python version of the challenge is a learning experience for sure. Oh, and I do need to add some more narration. Thanks for joining me, guys. Now you get to watch me type. You're very welcome, Sleepy John. Kernels. Thanks for joining, Arsmel. Oh yeah, I will definitely look into that, Padma. Yeah, and I think you posted a question in the forum topic as well, right? I think I saw that this morning. I was like, oh, I will do that once I get to work. Yeah, and please share the URL here. People are really good about helping out. I've been really delighted by how the community has come together to help each other out. Oh, and I do need to make this public so you guys can get at it. I'm just going to copy and paste so I don't have to type again. Markdown. Okay, I see. So you're trying to bin by a specific date. I see. Let's see. Let me finish this typing and then I will go take a look at it. STATISTIC. Oh, yeah. Alright, that one is ready. I'll publish it. Alright, so let me check it out. So binning for the histograms, I'm assuming, is what you're looking at? Yes, bins do have to be numeric. So it looks like what you actually want to do is a bar plot, probably. Yes, so we're actually going to do that tomorrow. To do a bar plot tomorrow. So I think that would be a really good example for this. You could also do a box plot, which, let's see, box plot. So if you're interested in how things change between quarters, I think a box plot over time is really nice. So let's see, box plot plus timeline. So a histogram is not the right type of choice for this particular data question that you are asking. I really like things like this for that sort of thing, where you're interested in how a value changes over time. So these are, well, this is an R example. I would also definitely use R for this personally, just because that's what I'm familiar with. So this shows the range are the whiskers. Usually, sometimes they're the interquartile range, and then the black bar is the mean. So you can see how the mean changes over time, but you can also see how the range changes over time. So I think that's a really nice way to look at changes in a numerical value over time and be able to compare them and sort of get an idea of what they look like. Another thing that you might look at is a violin plot. And I like these because they're sort of a compact way to show a lot of information. And picking visualizations is in and of itself a particular skill set. So and this is what a violin plot looks like. So it's sort of two density plots, sort of like mirrored over the center line. So it's another good way of seeing that. So you can see here the median is sort of moving around, and you can see that sort of it's a little bit more, there's a little bit less variance here, there's a little bit more variance here. So I don't know, just some ideas to think about. Yeah, but for the specific question that you're asking, I wouldn't recommend a bar plot, a histogram rather. You could also do the colored histograms that we were doing, so where each quarter is a different color, so like this. Yeah, and Sleepy John is recommending Seaborn for that, which I haven't used, but I've heard some very good things about. And actually for the challenge, I've seen some really nice work that people have done in Seaborn. So yeah, but you might wanna hold on to these for tomorrow, because we are going to be doing bar plots, and I think this would be a good, potentially a good way to apply them. All right, now I do have to get going. I got real work. All right, and I'm gonna make sure to make this public. And I'm also, if you want to go back and look at my other notebooks, I am posting them in the forum. All right, well, thanks so much for joining me today, guys. I had fun. I learned something. I hope y'all learned something, and we will see you tomorrow for categorical data. Woo!